All right, hi. So welcome to the MP 2.0, number 3, lecture 2, the MP 4.0. Wrong number. Anyway, so this is the second number 3 lecture. And so first of all, we'll start with an exercise. And so we want to find the last digit of 7 to the 17, the 17 to the 17. So let me find the last digit. So we can see that 17, so the last digit is 7. And so in terms of perfect powers, it goes 7, 7 squared is 49, 9, then 9 times 7 is 63, so 3, and 3 times 7 is 21, so 1, and then 7, 9, 3, 1, and so on. So it repeats in cycles of 4. So really all you do is write 17 to the 17 to the 17 mod. And this is just 1 to the 17 to the 17 or 1 mod. And so that means that the last digit must be the first number in the cycle, which is 7. So the answer is 7. And so that's the first exercise. So under exercise 2. So what is a 22nd positive integer n such that 22 to the power of n ends in a 2? And this is in when everything's written in base 10. So yeah, so I'll start explaining the solution now. So the last digit of 22 to the n is basically the same as the last digit of 2 to the n. And so that just repeats 2, 4, 8, 6, 2, 4, 6, 2, 4, 8, 6, and so on. So once again, it's every 4. So 1 works, 5 works, 9 works, and so on. And of course, the 22nd term of this arithmetic sequence of 159 so on is just 85. Because the formula is really just for the nth term, it's 4n minus 3. And so now let's move on to exercise. So now let's start going over exercise 3. So what is the smallest positive integer n such that 2013 the power of n ends in 001? So sorry. So first we can see that 2013 to the power of 100 is converted to 13 to the 100. And this is 10 plus 3 to the 100th. And so that's just basically 3 to the 100th. And that's because everything else will have at least a factor of 1,000, because the two terms that do not will be multiplied by. So there are two terms that will not have a factor of 10 that is greater than 1,000 in the binomial expansion. And so there are 10 squared times 398. Well, and then the term here and the binomial coefficient is 100 choose 2. And the other is 10 times 3 to the 99 times 100 choose 1. And here 100 times 10 is 1,000, so this goes away. And 100 choose 2 is 5,050. Sorry, no. But yeah, it should be 4,950. Sorry. Yeah, so 100 choose 2 is ended 0, so 10 squared times another factor multiple of 10 is also 1,000 times something. So this is compared to 3 to the 1,000th. And we can see that 3 to the 10 is converted to 49. And this, you just kind of have to bash out on your own. And so this is congruent to 49 to the 10. And 49 squared is congruent to 401. That's 401 to the 5th. And this is 401, or 400 plus 1 to the 5th. And if you expand this out, you can see that this is just 1 mod 1000. And so that tells you that n divides 100. Excuse me. Okay, sorry about that. So, yep. So you get that n divided 100. And so next, all you can see is that 2013 to the 50 is congruent to 10 plus 3 to the 50. And then, so this, and then you just do steps quite similar to the one over here. And you eventually get that this is congruent to 249 mod 1000. This is basically just mostly copy. And the final step is 2013 to the 20. And so you also use the same thing. 10 plus 3 to the 50. Sorry, 10 plus 3 to the 20. And this is congruent to 801 mod 1000. So that tells you the answer is 100. So the way this solution works is basically you kind of first have to notice that 100 works. And then after that, you have to, so for this kind of problem, once you have that a certain number works, then you have to show that all factors of it do not work. And if the number is of the form P1, E1 times P2, E2, so on, Pk to the Ek. So then the numbers you will have to test to check if any factors work is the number n divided by P1, n over P2, all the way to n over Pk. All of these could be possibilities. And these are, and you need to test through all of these in order for it to work, because otherwise there's a possibility you miss out on some number. So yeah. And if none of these work, then the number in question must have all of P1, P2 to Pk. And so yeah. Sorry, must have all of P1, P2, Pk to included at their original powers of n. And since n itself works, then it's fine. And it works. And so now let's move on to exercise. So now start going over number 4. So given that there are 24 prime between 3 and 100 inclusive, what is the number of ordered pairs P8 with P prime and P between 3 and 100 and A between 1 and P such that this sum is not divisible by P? So first off, if A is equal to 1, then this sum is just P minus 2 factorial. And it never works, because this is never divisible by P. And that's because P itself is prime. Sorry, I didn't mean that this fails. I just meant it's never divisible by P. And so this actually works. Sorry. And so there are 24 odd primes between, there are 24 primes from 3 to 100. And so that means that there are 24 solutions of the form P1. Now, if now suppose A is greater than 1 and is still less than P. Then, so you can see that the A over A minus 1 term, sorry, I forgot to write this. So the sum is A plus A squared plus A cubed plus A to the P minus 2 factorial is equal to A times 1 plus A plus all the way to A to the P minus 2 factorial minus 1. And so this is just A times A to the power of P minus 2 factorial minus 1 over A minus 1. Or A over A minus 1 times A to the P minus 2 factorial minus 1. And so then we can see that we can actually ignore this term because A is greater than 1 and less than P. So either way, it will not affect whether the sum is divisible by P or not. So we just need to look at A to the power of P minus 2 factorial minus 1. So if P is 3, then the sum is just A. And so that means that 3, 2 is a valid solution. And so that's because the only number between 1 and 3 is 2. And so next, if P is equal to 5, then the sum is A to the 6 minus 1, x congruent to A squared minus 1. And if we multiply this by A over A minus 1, this is equal to A times A plus 1 mod P. And so if we plug in A equals 2, 3, 4, all of 5, 2, and 5, 3. So far, those are our solutions. And so if P is greater than 5, then it is definitely true that P minus 1 over 2 is definitely not 2. And so we also have that 2 divides P minus 2 factorial. And so then P minus 1 over 2 divides P minus 2 factorial over 2. Hold on. Sorry about that. So yeah. So what you get next is that this is true, and it's because 2 and P minus 1 over 2 are between 1 and P minus 2. And so that means that P minus 1 always divides P minus 2 factorial. Because you can multiply P minus 1 over 2 and 2. And that gets you 2. And so by Fermat's little theorem, you can see that this means that A to the power of P minus 2 factorial minus 1 is equal to 0. And so there are no more solutions. So there's 24 plus these 3, circled in blue, so 24 plus 3. And so the answer is 27. And so now let's move on to exercise 5. So now start going over number 5. So we want to find the remainder of 109 times 99 times 999, although the 999 is divided by 1000. So make a note here is that 999 and all subsequent terms are congruent to -1 mod 1000. And so the number of nines, the number of integers here is just 999 minus 3 plus 1, which is 997. So that means that the integers, these multiplied out, is just 9. And so the expression is 9 times 99 times -1, which if you just multiply out is -891 or 109 mod 1000. So that's this question. So now we'll move on to exercise. So now start going over numbers. So I want to find the sum of all prime p such that p is the form a to the fourth plus b fourth plus c to the fourth minus 3 for some primes a, b, c. So not all of a, b, c can be odd, because if all of them are odd, then p is 2. And at the same time, if p is 2, then you get 5 is equal to a fourth plus b fourth plus c fourth, which definitely can't hold true for integers a, b, c at all. Or at least any positive integers a, b, c. And so at the same time, not all of the ABCs can be equal. Not all of the ABCs can be equal to 2. And that's because if it were, then P would equal 45, which you can tell is not going to work out, because it says prime here. And so that means that exactly 1 of ABC is 2. And so we just want to find the sum of all P. So ABC themselves don't actually matter much in terms of orders. So just without loss of generality, let A equal 2. And so then you get that P is equal to B to the fourth plus C to the fourth plus 13. And if you look mod 3, you can see that X to the fourth is always 0 or 1 mod 3. So 13 is congruent to, I just noticed. Okay. Mod 3. So 13 is congruent to 1. And so that means that B and C cannot both be 1. Or sorry, B the fourth and C the fourth cannot both be 1 mod 3. And so if X to the fourth is equal to 1 mod 3, it means that X can either be 1 or 2. So that basically means that one of B or C must be 0 mod 3. And we have that A, B, and C are all primes. So one of B and C is 3. And so once again, the order doesn't matter much. So we can just let B be the one that is 3. So then we get that P is equal to 94 plus C to the fourth. And so now we test mod 5. So C to the fourth is congruent to 1 mod 5 if C is not 0 mod 5. And that would give you a multiple of 5, which is clearly not going to work at all. Because the only multiple of 5 that is prime is 5 itself, and that will not work because that would imply that C is sub-negative, and primes are never negative. So we must have that C is equal to 5. And upon doing that, plugging that in, you get that P is equal to 719. And if you check, 719 is actually prime. So the sum of all prime P that work is 719. Although it says sum, but in reality, the answer is just one number itself. All right, so on to the next exercise, which is number 7. And so, yeah. So now I'll start going over this question. So find 3x squared, y squared, if x and y are such that this equation holds true. So we can move everything, all the x squared, y squared terms to the left side. So you get that 3x squared, y squared, plus y squared minus 30x squared equals 517. And so if you factor this, you can get 3x squared times 3x squared and y squared. And so this is plus 1, and this is minus 10. And so this is equal to 517 minus 10 is 507, or 3 times 13. And so x and y are integers. So this is never a multiple of 3. So also 160 if you check. So there's no multiple of 3, so it's either 113 or 160. So first of all, if so first of all, if x 3x squared plus 1 equals 1, then you can see that y squared minus 10 would have to be 507, and then y would be the square root of 517. And that's not a square. So this doesn't work. The next case is if 3 squared plus 1 equals 169, and then that would get 3x squared equals 168, and this just turned into x squared is equal to 56. And that's not a square, so this doesn't work at all. So the next final case is if 3x squared plus 1 is equal to 13. Then x squared is equal to 4, and so x is equal to 2. Actually, you don't need x equals 2. You just need to know that x itself is an integer. And so that tells you that y squared minus 10 is 39. And so y squared is equal to 49. And that would tell you that y is 7. But we want 3x squared y squared. So instead of directly solving for x and y, we can just use what we already have here and get that 3 times 4 times 49, which is 580. So that is the answer to this question. And now we can move on to the next and final question. So now let's look at this last question. I want to find the largest integer n that satisfies the fact that n squared is the difference of 2 consecutive cubes, and 2n plus 79 is a perfect square. So n squared is equal to m plus 1 cubed minus m cubed. And so this is equal to 3m squared plus 3m plus 1. And so this can also tell us that 2n plus 1 times 2n minus 1 is equal to 4n squared minus 1. And so this is 12m squared plus 12m plus 3, or 3 times 2m plus 1. And both of these are odd, and their difference is 2. That should be plus. It's not quite clear. And so, well, these are odd, and their difference is 2, so they're relatively prime. But since their product is 3 times a square, one of them is a square, and the other is 3 times a square. And the reason it can't be different factors is the reason the factors must definitely be completely different is because they are coprimes. And their coprime would mean that every single prime factor is either in one of the two. And none of the prime factors are shared, so yeah. And so if 2n minus 1 is equal to 3 times the square, then that would mean that 2n plus 1 is going to be 2 mod 3. But a square is never 2 mod 3, so that is impossible. And so that means that 2n minus 1 is a square, and so we can let that be b squared. And at the same time, 2n plus 79 is also a perfect square, so we can let that be a squared. So then a squared minus b squared, the difference of the squares, which we can just directly write as a plus b times a minus b, is just b. So these two have the same parity, and the product is even. So both are definitely even. So if we want to find the largest n, all we need to do is just maximize the value of, or we can, and to maximize the value of, maximize these values, so we can just try to maximize the sum of these two factors, because it's a times b, it's a plus b times a minus b, sorry. Actually, and to maximize the value of b, we just need to maximize the difference between these two factors. And so we also need to check that the value for m is an integer. So to maximize this, we can just have a plus b equal 40 and a minus b equal 2. And so that gives that a equals 21 and b equals 19. And so the result is, okay. And so the result is that 2n plus 79 is equal to 441. And so n is equal to 180. And as for m, so we can see that m is equal to 104. So n equals 181 does indeed work. And the process we have gone through above is all in order to maximize the value of n that we get. So the value of n we have is the maximal and is 180. And so, yeah, so that's all the exercises. And so that's it. And so have a great night. And I wish all of you have a nice rest of your weekend. And so thank you and bye.